Hello, everyone. I'd like to talk about molecular polarity. In other words, whether a molecule is polar or not. And the way we talk about polarity, or what we need to consider, is actually two big things. But polarity always comes from the distribution of electrons. Okay, so if the electrons are not evenly distributed across a molecule, whether it's a long molecule or it's just a short little binary molecule, if they go to the right, then that side is slightly negative because it has the essence or the feeling of negativity, I suppose you could say it that way. And the other side would be slightly positive. And of course, if they go to the opposite side, then that side would be slightly negative and the other side would be slightly positive. Okay? So as you can read here, the distribution of electrons is a big deal. Okay? And the strength of that is called the dipole moment. Now, we won't talk too much about dipole moments. I think I briefly introduced them in another video. But two factors that contribute to whether a molecule is polar or not is, first of all, the polarity of the bonds. For example, if I have a carbon-chlorine bond, that's a polar bond where this side is slightly negative and this side is slightly positive. Okay? But what if I have another carbon-chlorine bond? Then they seem to cancel out. What if I put another? Now, these cancel out here, but this one's polar in this direction. There's the dipole moment. But what if I put another one down here? So the polarity of the bonds, first of all, you need polar bonds in order to have a polar molecule. But like I just mentioned, even though they're all polar, sometimes they can cancel each other out. So it does not necessarily guarantee polarity. So the second thing is not only the polarity of the bonds, but also the symmetry of the molecule itself. Okay? So to be a polar molecule, you have to have an asymmetrical molecule to ensure that these electrons are not distributed evenly, okay, or to ensure an uneven distribution of electrons, okay? So keep that in mind as we move through, all right? Now, certain shapes are always asymmetrical in nature, okay? Now, we're going to get to the Vesper theory, okay? And we'll talk about bend, trigonal, pyramidal, T-shaped, seesaw, square, pyramidal. As you can read here, these shapes do not allow the molecule to be symmetrical. So, in other words, there will be a natural drifting of electrons to one side or the other, causing a polar molecule to result. So, what you see here, this list here, bent, trigonal, pyramidal, T-shaped, seesaw, and square, pyramidal, they're always asymmetrical. These shapes will always be polar. So, the shape in this case leads to an asymmetry. And the asymmetry allows the molecule, the electrons, to drift to one side because there's not a balance. So asymmetry and polarity can result from a heterogeneous group of atoms attached to the central atom, thereby creating asymmetrical differences in electronegativity. CHCl3 is a classic example. So notice we have a very symmetrical molecule. So this is a tetrahedral molecule. Okay, this is a Vesper theory that's very tetrahedral. However, this pulls in this direction, this pulls in this direction, this pulls in this direction. But this is relatively nonpolar, okay? So in other words, if all the electrons are coming down this way, this side must be slightly negative, leaving this side to be slightly positive. So in other words, there's, again, two things to consider. Even though we have symmetry in this case with this carbon atom making a tetrahedral molecule, it all depends what's bonded around that central atom. So the first thing you need is uneven distribution of electrons, okay? Electronegativity differences. In other words, a polar bond. But the bonds could come together in a way that could cancel each other out, thus leading to a nonpolar molecule. In other words, this would be a nonpolar molecule. Okay, or perhaps the CCl that I gave you. Okay, those are nonpolar. But if I make one change, now it's quite polar in this direction. Okay, so even though the symmetry says, oh, this is balanced, you could be unbalanced depending on what's bonded around that central atom. So again, we will keep beating this up as we move along here. If the molecule is asymmetrical, the more polar the bonds, the more polar the molecule. Okay? So if we take a look at this right here, and they give you some numbers for dipole moments, we see that H2O is more polar than H2S. And there's a reason here, okay? Oxygen is more electronegative than sulfur, okay? So they're both, this is a polar bond, this is a polar bond, this is a polar bond, this is a polar bond. So now you have polar bonds, check on that one, on that first thing, but they are asymmetrical. Bent molecules are always asymmetrical, okay? I'm sorry, bent molecules are always asymmetrical and thus always polar is what I like to say. So even though they're both polar molecules, this one is more polar than this one is over here. Okay, and the reason is because oxygen has a stronger electronegativity value, thus making these two bonds, this bond and this bond, more polar, thus pulling the electrons more towards this direction, making this side slightly negative and this side slightly positive. Over here, hydrogen sulfide, H2S, is not is also a polar molecule, but I'll draw small. It's not quite as polar. Okay, so yeah, there's varying degrees of polarity. It's not a black or white situation. It's not a yes or no situation. Okay, so both molecules are asymmetrical and exhibit dipole moment, but the water's dipole moment is significantly higher than the hydrogen sulfide due to the greater electronegativity difference between oxygen and hydrogen. Okay, so what I'd like to do is do a couple practice problems and revisit polar and nonpolar covalent bonds. So which of the following is true regarding molecular polarity? Okay, see what you can do here. Pause the video when you need to. There's the answer. Which of the following explains the dipole moment of CCl4 having a zero dipole moment? In other words, it's a nonpolar molecule. There you go. Which of the following bonds is most polar? I don't have answers here, but if you want to pause and try it, I'll show you the answers. Which of the following bonds is most polar? You're going to default to, these are all pretty close. It's either A or E. And this is actually somewhat of a trick question. Gallium chloride is actually a little bit more polar because gallium's a metal. Okay, so actually that's the correct answer. If this wasn't there, this is the easy answer. Okay, because chloride's involved. Which of the following bonds are most polar? Okay. So they all appear in a square. So S, SE, Cl, and Br all appear in the same square. Okay, so you're looking for a top, right, bottom, left. So you should guess this one being the correct answer. Okay. Which of the following bonds is more polar? Now we're looking for a distance of separation here. So CLF is polar, but IF is more polar. Okay, greater separation on the periodic table, which means a greater electronegativity difference. Okay, so what I want to do now is let's go back and look at these polar molecules once more. Okay, so there's two kinds of polarity, it's polar molecules, and that is based off of the electronegativity differences. You can see the gradient once more down here. Okay, I make mention of in class that the bonds are never purely ionic or purely covalent. Okay, there's always some gradients. There's also some difference in there. There's always not difference. There's always some one of the other kind is in there because we cannot assume complete 100% transfer of electrons. Electrons are very mobile and they move quite a bit, guys. Okay, so here's how electronegativity values differ. Top right is obviously the highest. So polar covalent bonds obviously have this polarity where the electrons like to drift to the left here in the OH bond, making that side slightly negative and the right side slightly positive. So this is a polar bond. This is a polar bond. This would be a polar bond making a polar molecule because it's just the HCl is not only is a polar molecule, it's because it has a single polar bond. Okay, Cl is more electronegative than H. Okay. By the way, we will not worry about magnitude of the dipole moment. Okay. So which pairs of atoms will form a covalent bond? See what you can do here. In which case, which bond is more polar? Okay, pause the video when you need to. Okay. BCl and CCl are both polar, but BCl is definitely the more polar bond. Okay. There's a greater separation between B and Cl versus C and Cl. Okay. PF or PCl, anytime you see, so this is a constant, but F is involved, so that's the more electronegative, and that is a greater separation of electronegativities. Which atoms would form the most covalent bond? I'm sorry, which one would be the most covalent bond? There you go. And the last thing I want to talk about in this video is nonpolar covalent bonds, which is right here. Okay, so again, with nonpolar covalent bonds, we're going to have electronegativity values that are less than, 0.3 or less. So the easiest thing to consider with this is Professor H bond click, H2, Br2, O2, N2, all those types of things. Since it's the twinning effect, even though they both have the same electronegativity, because they have the same electronegativity value in these two, the electrons, it doesn't matter where the electrons go, it's very similar. So this blob right here shows the electron cloud. And the fact that the electrons don't want to drift here or here, so it makes no poles, okay, at least on a normal, everyday consideration. All right. However, let's say the CH bond is considered to be a nonpolar bond. It's important to know. It's important to know that the CH and the CH bond, which is quite common in organic chemistry, is a nonpolar bond. Okay. So here's a nice breakdown of everything. Notice right here we have our nonpolar covalent bond. This is the electron cloud. It's very evenly distributed. This is a polar covalent bond. Looks like the electrons like to be around here more than they like to be around here, making this side slightly negative. This side, of course, slightly positive. Ionic. Of course, we see a complete transfer of electron. Of course, where did the electron come from? The electron came from the positive cation and was transferred to the negative cation, negative anion. So which one had the greater electronegativity? The one on the right or the one on the left? It is this one had the greater electronegativity, and it had a much greater electronegativity. Okay. Notice down here it's the same argument. Okay. So you can check that out when you want to. And we've already covered this, so I'm done with this video. If you have questions, go ahead and ask.